Hi everyone, and welcome to this video where we will show you how to create a face-centered cubic or FCC unit cell using a Rhino Grasshopper. It involves a fully parameterized unit cell geometry to control its implementation into larger and more complex uniform periodic lattice structures. An FCC or face-centered cubic unit cell is a cubic structure with lattice points at each of the 8 corners and at the center of each of the 6 faces of the cube. This arrangement creates a highly efficient or tightly packed structure to create lightweight and strong parts by arranging material and a complex three-dimensional lattice-like pattern. Of course, we construct a specific face-centered cubic lattice structure in Rhino Grasshopper. The key is to connect each corner point of a cube to the centers of the 3 adjacent faces. Let's get started with running the Grasshopper tool. And before we begin geometry parameterization, we will enable the bifocals component here to display all component names in the Grasshopper canvas or working space. The first conceptual breakdown of the structure represents the nearest neighbor connections in an FCC unit cell, which has 2 design features. It is 8 corners of a cube and 6 centers of each face of the cube. First, we need a cube to define the boundary of our unit cell, and for that purpose, we introduce a central box component, which we are placing it at the canvas. Now we have to add a number slider which boundary values from 1 to 10, and as the default value we set 5 units or 5 points for each direction of x, y, and z of the cube, as you can see on the screen. So this component will be our main command to control overall cell size and its dimensions. Now we need to extract the 8 corner points and 6 face center points from our cube, and for that purpose we will use a new command. It's deconstruct brep and connect this command with our previous command of central box. This component gives us a number of vertices, or to be more precise, an output that gives us the 8 corner points as well as the number of faces, which gives us the 6 faces of the cube. Further, we need to introduce area component to find a central point or middle points for each of the 6 faces that create a cube. And also the output of the area named centroid is our main goal to take or to achieve a 6 middle or central points for each face. Next, we have to find the connections So this is the core step, because for each of the 8 corner points we need to find the 3 closest face center points. And for that purpose we introduce a new component named closest points. And we connect the vertices output of the construct brep to the P, or point to search from input. This is our list of 8 corners. After that we connect the centroid output from area command to C input, or cloud of points to search in. This is our list of 6 face centers. And final, we have to define count or number, which we will define by panel, where we just write in the number 3 and connect with an input or count. And this action also can be made by right click on n and set integer as a number of 3. So this is the same, but we will use a note where we define this number 3. The component will now output for each corner point a list of the 3 closest face center points. In next step, we draw the lines inside the cube. With the start and end points identified, we can now draw the connecting lines. And we introduce component line defined through 2 points, start and end point, where we connect vertices output, or V output of the construct brep component, to the component A, or start point of new command line. And the second point, or in point B, we connect with output P from closest points command. And to not forget, we have to do a right click on first input, input A, and we select a graph option inside a start point. Graphed data option is a crucial step that ensures each center point connects to its own set of corners. Grasshopper will automatically match the data, creating 3 lines for each of the 8 corner points, resulting in the 24 lines that form the structures. So, if we make a disabled preview here, we will see our main construction or wireframe of the unit cell. It rests to add some body to this our wireframe, and we will use a multipipe command where we connect our structure through the command line and curves as input of the multi-pipe. Here we want to control strut size of the unit. So using a panel command, we define a value for strut size. And now, as you can see, we have a fully parameterized unit cell with regularly formed nodes for each side of the whole structure. But if you can see here, the places where struts intersect each other inside the cube, there is no any kind of formed or created node. For that purpose, we can flatten output data from the line command, which holds our main wireframe of the structure. And if we do that, we will create additional nodes in those places. So we have created a unit cell with regularly created nodes for each intersection inside the cube. If we turn off this flatten option, this or these places of intersection will lost node creation, and we have a situation where struts pass through the bodies of each other or cross each other, and on these places we will not have any kind of node. But for a more complex analysis and integration into periodical uniform structures, we recommend to use a flat data and create nodes on those specific places. Now it rests us to create a baked model and to get a solid model ready for the further implementation into the periodical lattices. That's it.